Welcome back. We will now consider what we call the Leibniz formula. L-E-I, Leibniz formula, or Leibniz's formula, if you like. So, what is the usefulness of this? Leibniz's formula is used for getting the higher order derivative of a product of two functions. That is, it is like a product rule for higher order derivatives. That means if you want to get the nth derivative of a product of two functions, then Leibniz formula provides us with the tool for doing that. We know already that to get the nth derivative of a function, any kind of function, basically, we saw how it could be done. We would differentiate, get the first derivative, the second, the third, up to as many times as possible for us to see a pattern. Okay, and then we generalize the pattern. That works fine for most cases. It's just that it happens that when we have a product of two functions, it might be too complicated to go through that process. So Leibniz formula will come in handy in such cases. So to have an idea of what this is about, we know that if we have a product of two functions, let's say that we have two functions u and v, for instance. These are both real valued functions. So let's say that they take elements from subset I, which is a subset of real numbers, and produce some real numbers as we have them here. So for this function, we know from what we've done before that if we were to take the derivative of this with respect to x, derivative of the product of these two functions, we know that both of them are functions of x. So if we want to take the derivative of this product from what we have done before, it was going to be, we would keep one of them as constant, differentiate the other. So this will be u, the v, the x from our rules of differentiation, and plus v, the u, the x. So this is quite easy to deal with because this is just the first derivative. So it's quite straightforward to just get the result and move on. So that means that basically we already know the uv. So if you want to get the uv, it is going to be u dv plus v du. That is, we're using this notation now. Instead of writing the dx, we're writing the big D. So instead of writing the dx of v, we write d of v. So instead of writing the dx of u, we write d of u. So that is basically what it is for the first derivative. And if we try to get the second derivative, so let's say we want to get the squared of uv. So that is going to be the uv. So we have the uv up here, so we'll then differentiate it. This will be the derivative of u dv plus v du. And we know that for us to complete this, what we have here is what we have out here is itself a product of two functions. That is, u dv is a product of two functions because we expect that the derivative of v could also be a function of x. So this is itself a product of two functions. So for each of these portions, we will have to differentiate applying the product rule in terms. So we will keep u as constant. We will keep u as constant, then differentiate the v. That will be the square of v, and then keep the v as constant and differentiate the u. That will give us the u multiplying the v. So that will be the derivative of this, then plus the derivative of this. So keep v as constant and differentiate the u. That will be v the u, or say the square u, and then keep the u as constant, differentiate v. That will be plus the v du. So it's quite easy, and we can easily rearrange this or rewrite this. If we write this, we observe that this is equal to u the squared v, then this is the u dv and this is the v du. They are the same things, so we can put them together, we can add them up. That will be 2 multiplying the u dv. Okay, so that is the same thing as the v du. So putting them together, then plus v multiplying the squared u, and that will be our second derivative of this product, the squared uv. So let's follow the pattern like that. This is for our first derivative, so we can call this equation 1. This is for our second derivative of the same product. We can call it equation 2. If we proceed to get the third derivative, that's the cube uv. That will be the squared uv. So that means it will be the derivative of the squared uv. That's derivative of what we have up here. And that will be derivative of, so let's put all of this here. That will be u the squared v plus 2 the u the v plus v the squared u, and that's what we have up there. And so to simplify this also, in the same manner, we will observe that what we have here is also a product of two functions, because the square v could possibly be a function that depends on x. So we take this as a product of two functions. You can differentiate u first, keep the square v as constant, or keep u as constant and differentiate the square v. That will be derivative of the square v, that will be the cube v. Then keep the square v as constant, differentiate du, that will be plus du multiplying the squared v, and we'll move to the next term. Plus 2 is constant, so let's say we are keeping the u as constant also and differentiating the v, that will be plus 2 du multiplying the squared v. Then let's keep the v as constant and differentiate the u, that will be plus 2 the squared u multiplying the v. Then we differentiate this last term, so we can keep v as constant and differentiate the square u, that will be v multiplying the cube u. Then keep the square u as constant and differentiate the v, that will be plus the v multiplying the squared u. And if we tidy this up, that is put together the like terms, we're going to have this to be u multiplying the cube v. Then the next one here is du multiplying the square v. So is there any other thing like that? We see this is also du multiplying the square v, so we can put these two together. That will be plus 3 multiplying du multiplying the squared v. So we have taken this and this, we have taken this already as well. Then the next one is the square u the v, so we can see the square u the v here, and this is the same thing as the square u the v, so we can add this one the v the square u to this 2 the v the square u, so that will give us another expression. You can say this is 3 the squared u the v, and that takes this and this. Then finally we have plus v the cube u. So that's about that for the third derivative, okay, of the product of these two functions u and v. So we can already observe a pattern here, which is the point of the Leibniz formula. And the pattern we can observe here is the fact that we have this to be u. Look at the first derivative, we have this to be u multiplying the v plus v multiplying the u. So we can see that for the first derivative, so let's just write them out here, okay, so that we can easily observe the pattern here and how we came about the whole idea. So for the zero of uv, that's when it is not differentiated at all, that's just uv. So what we have here is just 1 uv. And for the 1 of uv, that's the first derivative, we add this up here, we add the this one to be 1 that is the coefficient. So we just want to pick on the coefficients first. Let's pick on the coefficients. So this is 1 okay, let me extend this, we're talking about this one. And for the squared uv, we can see we have the coefficient to be 1 2 1. So the next one is actually 1 2 1. And for the third one, which is the cube uv, this is what it's doing here. The third one is this the cube UV. Okay, this is for the second one. This is the third one, and we've seen that this is 1 3 3 1. So this is going to be 1 3 3 1, and that is everything we have for this. So this is obviously what we call the Pascal's triangle. So we can see that the coefficients here, this one was 1 1. If we put this together, 1 plus 1 will give us 2. Then we add 1 1 to the extreme. Then 2 plus 1 will give us 3. 2 plus 1 will give us 3. We add 1 1 to the extreme again. And we can keep getting the coefficient like that. If we add 1 plus 3, it will give us 4. 3 plus 3 will give us 6. 3 plus 1 will give us 4. Then we add 1 1 again. This is expected to be the coefficient of the subsequent term. Okay, and so we have a pattern to observe here, which is a Pascal's triangle, which is given by combination. Okay, so we should recall the idea of combination. If we take, for instance, n combination R. So you should recall this idea, which we are going to use here, and which is the a major part of the Leibniz formula. We should recall that when you have n combination R, that is the same thing as n factorial over n minus R factorial multiplying R factorial. So basically, that is the idea here. That is how we came about all of these coefficients. If you want to get this coefficient, then we can always take that n factorial. So for this third one, for instance, this third situation here, when n is 3, we see that this expression here is the same thing as n combination 1 or n combination this is 0 1 2 3. So this will be n combination 0, this will be n combination 1, and this will be n combination 2, this will be n combination 3. Our n here is 3, so basically this is just 3. So we can see this is 3 combination 0, 3 combination 1, 3 combination 2, 3 combination 3. So that is how we can obtain this coefficient. So it's quite easy to obtain the coefficients by taking n combination R. And we also observe that, so what we're trying to do here is to arrive at the general formula for getting the nth derivative of this product of two functions. And so to do that successfully, we will observe this pattern. We have seen the coefficient already is given by this combination, and when we look at all of this, we see that this is the same thing, for instance, as writing 3 combination 0 d to power 0 of u, then d to power 3 of v. So, and plus the next one is going to be 3 combination 1, then d to power 1 of u, then d to power 2 of v. Then the next one will be 3 combination 2, d to power 2 of u, then d to power 1 of v. So we can see that as we proceed from the first term to the last term, the powers of d for d that corresponds to u actually increases from 0 to 3. Uh, this is for first term, second term, third term. This is for this. The last term is going to have d, okay, 3u. V does not have anything, so that is d0 of v. So we can see that the expression for v, okay, the derivative we are taking for d, or the order of the derivative for v, is going from 3 to 2 to 1 and then to 0, whereas the one for u goes from 0 to 1 to 2 and to 3. So going further now, we will say that for generalization, we will observe that We did not pick any specific function u and v. We're just saying that this will be the general formula, okay, no matter what u and v happen to be. So far we have a product of two functions, we're able to identify those two functions, then we can always use this formula to obtain their derivative. So we now observe that if we want to take the nth derivative now of uv, so how do we get the terms? The first term will be n combination 1. Since this is third derivative, the third derivative will add n 3 combination 0. So this will be n combination 0. You can write it as n combination 0. Then we take the zeroth derivative of this. So we can say this is going to be d to 0 of u, then d to n of v, because just like this one we have this to be the third derivative where n is 3, and then we go further. The next term will be 3 combination 1 d to 1 of u, d to n minus 1 of v, because this one keeps decreasing from n up to 0. And then the next one will be 3 combination 2 d to of u, then dn minus 2 of v, then it goes on and on and on like that up to the last term. And before the last term we have this to be sorry, this shouldn't be 3 combinations, so this should be n combination 2 now, n combination 2. And then by the time we get to the last point, we see that it ended at 3. Where is this expression again? It ended at 3 combination 3. This is meant to be 3 combination 3. 3 combination 3. So it ended at 3 combination 3. And before that we had 3 combination 2. So basically we can write this as n combination n minus 1, then d to the power of, so it was the derivative for u, I mean the order of the derivative for u that was increasing. So this will have increased to n minus 1 of u, and this will be d1 of v. And then at the last point, we're going to have this to be n combination n, and that will be d of, for this one now, that will be dn of u, and d0, that's n minus n, which is 0 of v. So we can see that the order of the derivative for v has gone from n to 0, and the order of the derivative for u has gone from 0 to n. So it keeps decreasing like that. The one for u decreases, the one for n, the one for u increases from 0 to n, the one for d decreases from n to 0. And we see that for the combination also, this lower number increases from 0 to n. So that is the idea with the Leibniz theorem formula. We can then say that this is simply equal to, because there will be several other terms between this is simply equal to the summation of n combination, so we can say n combination r in this case, then the r. So we can see that when we have 0 here, we have 0 here. When we have 1 here, we have 1 here. So if we take r, then it will be the r of u, then multiply by the n minus r. So when we add 0 here, this was n minus 0, which is for this. This is n minus 1 when we add 1 right here. So this will be n minus r of v. So this is the derivative we take all through. And just that we have to start our r from 0. So this should start from r equal to 0 up to n. And this gives us our result. And this is what we call the Leibniz formula, because it gives us the expression required to find the nth derivative of this product of two functions, the two functions u and v. So this is the Leibniz formula. We'll make use of it to get the nth derivative of the product of two functions as we proceed. But it's important to know what each of these things mean, as we have just established right now. So let us formalize this statement. Let us present this statement of the Leibniz formula formally, then present a proof of it. Let's examine a proof of this statement using mathematical induction like we did for some other formulas we've obtained in the past. Okay, so we say that Leibniz formula. So we say let u v, okay, some functions that take in I, which is subset of real numbers, and produces r, some other real numbers. Let these two be differentiable functions of order n, differentiable functions of order n, whose values at x are u of x and v of x respectively. So differentiable functions of order n simply means that we can get the derivative up to order n. So that's what we mean by differentiable functions of order n. So those are the functions. Then we say that then the nth derivative, so if I are given these two functions which are differentiable up to order n, then the nth derivative of the product u of x, v of x is given by the formula dn of uv equals summation from r equals 0 up to n of n combination r dr of u, then the n minus r of b. So this is a formal statement of the Leibniz formula. So now let us examine a proof of this, okay, by mathematical induction. So proof of the Leibniz formula. Okay, basically we have seen how it came about from the illustration we had earlier, and now we want to do a proof of this by mathematical induction. So we now say that by mathematical induction. We proceed as follows by mathematical induction. So let's consider what happens for when n equals to 1. We know this is applicable to all n. Okay, so let's see what happens for when n equals to 1. So now set for n equals to 1. What is going to happen for n equals to 1? That means our d1 of uv, okay, going by this explanation, this should start from 0 and end at 1. Okay, so for this particular case, we can see that our n is 1. So using this formula, we should have this to be equal to the summation from r equals 0 up to 1, because our n is 1, of 1 combination r, then the r of u, then the r minus, so that's n minus 1, that's 1 minus r of v. And so if we are to go by this statement, this simply means summation. So for the first term, we set r equal to 0. So when r is 0, this will be 1 combination 0 of d to the power 0 of u, then d to the power 1 minus 0 of v. Okay, that will be the first term plus the second term. The second term will be when r is equal to 1. This simply means the summation will go from r equal to 0 up to r equal to 1. So the second term will be the final term, and that will be when r is equal to 1. And for that case, we're going to have this to be 1 combination 1 d to the power of r. R is 1 in this case. This will be d to the power of 1, then multiplying u, then d to the power of 1 minus 1 multiplying v. So with this, we're going to have this expression to be what is 1 combination 1? Of course, we can do this. We can solve it out and say 1 combination 0 is equal to 1 factorial over 1 minus 0 factorial, then 0 factorial. We know that 0 factorial is 1, so this is 1 minus 1. So everything here is going to be 1. And we can always do this combination also with our calculator. So let's bring up our calculator. We can see combination, that's combination sign somewhere around here. We see this is NPR, this is N permutation R, this is N combination R. So if you want to do 1 combination R, we'll press 1, then shift, then come here. So that is NCR, then put N combination 0. So that will give us our result, which is 1. And for the second part, we know we also need to do 1 combination 1. So we can easily check that here also. 1 combination 1 is going to be 1. Right? So that is that about that. So let's move on. So basically, this coefficient is 1. So this is 1 multiplied by the d to the power 0 is also 1. So that is just multiplied by u. Then d to the power of 1 minus 0, that's d to the power 1 of v. And this will be plus 1 combination 1, which you have seen is also 1. And this will be d to the power 1 of u. Then d to the power 0 of v. So that will be multiplied by v. D to the power 0 is 1. So this is 1 times v. So at the end of the day, we see that this is just going to be equal to u dv plus v du. Okay. And that is exactly what it is by product rule also. We know that by product rule, so we can take note of this and also observe that by product rule, we know that by product rule for real value functions, as we have established in the past, we know that the u v is the same thing as u dv, that is keep one as constant, differentiate the other, plus keep the other as constant, differentiate the first, v du. So that is b. So we know that what is provided for by this formula is the same thing as what we would have obtained if we differentiated ordinarily. Okay, using the product rule to give us this. So these two are the same, and that confirms that it is true. That is, the formula holds true. That is, this statement of the formula is true for n equal to 1. So the next thing to do, okay, by our mathematical methods approach, is to assume that it is true. Assume it is true for n equal to some m. And if that is the case, it means that the m, okay, of uv is equal to, so we just use the formula. In this case, we replace n by m in the formula. So this is going to be equal to the summation from r equal to 0 up to m of m, that's m combination r, then the r of u, then the m minus r of v. So basically, we're just saying that this expression here, when n is equal to m, we're just going to replace that n by m in this expression, and it gives us basically this. Of course, we know what this means. This is just saying that we have this to be this summation sign means that we start with r equal to 0, just like we did here, and then stop at r equal to m. Okay, so for instance, the first term will be when r equals to 0. That will be m combination 0 into d to 0 u, then d to m minus 0, which is m v, then plus m combination, we go to 1, and this will be d1 of u, then dm minus 1 of v, and plus say n combination 2. So that will be m combination 2, m combination 2. So let's write this properly. This will be m combination 2 of d2, then the m minus 2v, and that continues like that, and like that. And then the second to the last term will be, that's when this is, when r is m minus 1, that will be m combination m minus 1, and for this we're going to have d into m minus 1 of u, then that will be d1 of v, that will be m minus 1, that will be 1 of v. Then the last term will be when we have m combination m, then dm of u, then d naught of v. So basically this is what this summation is saying, so we just expanded it out here. All right, so if it is true for n equal to m, then this is going to be true. It means that the mth derivative of uv will be given by this expression. Okay, so that's all we need to do for the second step. And now for the last step, step 3, we will say that for this, we will say, let us check for what happens when n is equal to m plus 1. So that means for this situation, we're going to have the m plus 1 of uv. And the m plus 1 of uv, I mean, that is the same thing as d of the m of uv. Okay, so this is uv, please. This is uv. So we have u and v. So that's what this means. That you can just see that as d to power m plus 1 is the same as d to power m multiplied by d to power 1. So that is the, you can arrange that as the derivative of the mth derivative of uv. And now we already know what this is from up here. So we are just going to put in what we have up here. We'll put that right into this and then expand it and see if it is going to confirm that it is the same thing as what will be provided for by this formula. Okay, so let's add an additional page to see what we are driving at. The point is that if this formula is correct, then we expect that the m, if the formula is correct, we expect that the m plus 1 of uv would be equal to, so we just put m plus 1 here. So we just replace m here with m plus 1. So that will be m plus 1 combination 0, d to 0 u, then d m plus 1 v, and so on and so forth. And that will proceed like that. Okay. So if we are able to now make use of the result for m here, okay, insert it here, differentiate it normally using our product rule and everything, and we're able to simplify it so that at the end of the day it conforms with the what we would obtain using the formula directly, then that confirms that the formula is also true for n equal to m plus 1. I guess there's no need for this now. So let's just leave this out. Instead of repeating that, we just know that it is the same thing as having m plus 1 here. Wherever m appeared here, it will be m plus 1 instead. Okay. So going forward now, we will say that this expression here is equal to the derivative of, so let's put in all of this. We already know the m of uv from our assumption in step 2. So we're just going to insert that here. Okay. So this is going to be m combination 0 and the 0 of u, the m of v. So instead of writing this the 0, let's just leave it out. The 0 is just 1. So let's just write this as u the m v, then plus m combination 1 d u the m minus 1 v, then plus the next one is m combination 2 the squared u the m minus 2 v, then plus, and so on and so forth. Then when we get to the second to the last term, this is m combination m minus 1. Then we have this to be d m minus 1 into u, then the v. Then finally, for the last term, we have this expression to be plus m combination m dm of u. Then this is the 0 of v, that is just v itself. Okay, so let's write that first before this the m of v, so we don't mix them up. So this is v, okay, the 0 of v, that's just v, then multiplying the m of u. All right, so that is that about that portion. So let's close up this bracket. So let's try to expand each of the terms here and see if we can then simplify the results to obtain the same thing as what we have up here. All right, so we will say that this is equal to the coefficients are just constants, so we don't have a business with them, at least for now. So we can just move that out. For the first one, m combination 0, then we will have to differentiate this expression. So we can say this is n combination 0 into, we're moving this out, we want to differentiate this expression, and this will be a product of two functions on its own. So we can use the product rule again to expand this. So we can differentiate this first. When we do that, we are going to have du, then differentiate, keep this constant, that is the mv, then plus keep the mv constant and differentiate u. I mean, that's what we just did. Then keep u constant and differentiate the mv. That will be u, the m of this, that will be the m plus 1 of v. That is basically this is just saying that the m of v, that's d multiplying d to power m, that's d to power 1 multiplying to d to power m, that will be d to power m plus 1 v. So that's basically how we came about that when we differentiate the mv again. All right, so that is what we have from the first one. Then going to the second term, this is m combination 1, that is constant, just move it out. Then we have this to be du. So by the time we differentiate this now, that will be d squared u. So this will be d squared u, then the m minus 1 v. All right, so that's the first term. We've differentiated this while keeping this as constant. So the next thing is to differentiate this while keeping the u as constant. So that will be plus the u is constant, derivative of the m minus 1, that will be the m, okay, that's d multiplying d to power 1 multiplying by d to power m minus 1, that is d to power m minus 1 plus 1, that is d to power m of v, and that is what we get from this second part. Okay, so the pattern continues like that. Let's go to the third term just to see how all of these things will play out. And this is m combination 2, then the squared. So for this case, we'll also take the derivative. By using this, we'll expand everything. So the derivative of this, that will be the cube u, then plus, multiply by this, that is the m minus 2v, and then plus differentiate this. Okay, so that will add 1 to this power, that will become m minus 1. This will remain the same, that will be the squared u, the m minus 1 v, then close the bracket, and then the pattern continues like that. So when we get to the second to the last term, we're going to have the same thing here, move out the coefficient m combination m minus 1, then for the power, differentiate this one first, that will be d to power m of u, then keep this as constant, dv, plus, so this is in brackets, okay, then plus keep the m minus 1 of u constant and differentiate dv, that will be the m minus 1 of u, then the squared of v. So we can close the bracket on that. Then we differentiate this itself. This will be plus m combination m, still the same. Then open up this bracket. Then we have v standing alone. When we differentiate that, that will be the v. So this will be the m u, then multiplying the v, then that's we've differentiated b, keeping this as constant. Okay, so we want to now differentiate the m. Okay, keeping the m u, keeping v as constant. That will be plus b into the m plus 1 of u, and then we close the bracket. So that's what we get when we expand this out. So don't forget, what we're trying to drive at is to actually check if we are able to, by simplifying what we just wrote out now, we're able to get an expression that is similar to this, except in the sense that m here can be replaced by m plus 1. Okay, so to proceed now, we say that this is equal to, for the first one, we add m combination 1. So this is m combination 1 still, sorry, m combination 0. Okay, and for this situation, we have, do we have like terms here? So let's identify if there are like terms. So for this is the MV. Okay, we also have the MV here. So this is the U, the MV, and this is the U, the MV. So we can bring them together under a single entity. So if you bring those two together, we're going to have this to be um, M combination, sorry, m combination 0. That's the coefficient of this first one. So we can write this as m combination 0, and then the coefficient of the second one there for our du dmv. I mean, that is every, that's all, that's the, those are the only two places we have this. The second coefficient there was plus m combination 1. So when we put these two together, then we use it to multiply the u, the m of v. Okay, so that tells us that this is gone. Okay, so I'm crossing this out so that we can identify easily the terms that we have made use of as we proceed. So that is that. Then the next one is u, the m plus 1 v. So we can see that u, the m plus 1 v is here. It is not here, it is not here, it is not in any other position. So we can just write that out as it is. Okay, so we can write plus, okay, I think this should come first before this one. So let me try to put it first. So this is equal to m combination 0. That means I'm writing this first, then the 0 u, okay, because this is u, okay, alone, not being differentiated. That's the same thing as having the 0 u, then the m plus 1 b. Okay, so that's what we have for this situation. We have this to be the m plus 1 b. So there is no other point like that that has the n plus 1 v. So we don't have any such other term. So we just leave this as it is. Okay. Then the next thing is that we will get our other term. So basically, we are done with this also. All right. So the second term is this du dmv, which is this expression and this expression. Okay, so we've put the two together and added their coefficient. This is m combination 0 plus m combination 1. So we're good with that. Then we look at the next term. If there are other terms that we can put together, this is the square u, the m minus 1. So the square u, the m minus 1, and that is the same thing as what we have here, the square u, the m minus 1. So if we put those two together, we're going to have this to be plus, so the coefficient for this is m combination 1, and the coefficient for this is n combination 2. So this is m combination 2. So m combination 1 plus m combination 2. Then we can write a single one of them. That is the squared u d m v. So basically, that is that about that. And so that takes off this term and this term. So what do we have left? We have this term. Okay, it appears we cannot add it to any other thing. Okay, I mean, we have this term left before this other one. So it appears we can't add it to any other thing, but it happens that if we were to write the next term after this, we will have an expression that is similar to this that we can put together. Okay, so for now, we'll just leave it as it is here. Okay, to avoid complicating our sum. So this is going to be plus. Then looking at the second to the last expression, so we look at what is also similar to these expressions. Yeah, these last four are two expressions. We'll see the mu the v. That is the same thing here. The mu the v is here. The mu the v is here. So we can put those two together. That will be plus m combination m minus 1, then plus m combination m. So put these two together, and this is the mu dv. All right. Then finally, what else do we have that are similar here? We have the m minus 1 u the square v. Okay, the m minus 1 u the square v. We can see that we don't have exactly that here that we can add together with it. All right, so we can leave this out just like we left this where's that again, just like we left this one out. So we can leave this the way it is. It is meant to be added together with the one that precedes this. Okay, but we have not included it here because we just picked some of the terms. Okay, we just want to observe the patterns and write this out. So for the final expression, we say we are ignoring this just as we ignored this. So let's leave it like that. And for the final portion, we will have this expression. So we can see that finally we're going to have plus m combination m into the m plus 1 u. Okay, v multiplying the m plus 1 u. So we can write that as the m plus 1 u, then the 0 v. So this is all that we have so far. And don't forget that to get to this point, there are several other terms in between, okay, that we have ignored, but they will have a similar pattern to this, okay. So the terms that we have left will have a similar pattern to this. That's why we just left them. So we have been able to observe the general pattern, the terms we have left to follow. All right. So with this now, let's see what does this give us. Okay, going from going along with what we have here now, what does this expression actually give us? We can see how we came about the expression. We started with m combination 0. M combination 0 gave us this, the m plus 1. That was the m plus 1 we got here. Just like we had the m here, it was the m that we have. Okay, and for m combination m also, it was the only one we had. So basically we have the same thing right here, m combination m and m combination 0. All right, so going further now, don't forget what we're trying to do. We want to simplify all of this and then see a pattern. If we can observe the pattern to be similar to what we would obtain by using this formula directly, then we will be able to conclude that indeed the formula is applicable and is true, or it is true, if you like, for n equal to m plus 1. So how do we go about that? Yeah, that should be, that is our concern. How do we go about establishing that now? So we can see m combination 0. So let's play around with something here. So don't forget our destination. For our destination, we can observe something here quite easily, that this is for u, the power, the order of the derivative goes from 0 to 1. This is du, so the u here is the 1u. All right, so for the derivative of the u, it goes from 0 to 1, then to 2, and then it continues like that up to m, then it ends at m plus 1. So that is good, an observation. Then for v, it goes from m plus 1 to m. You can see that it keeps decreasing, and then it gets to m again. So we have m here. This should have been m minus 1 for v. And for this, it eventually gets to 1 and then to 0. So let's check what we wrote out here. Let us check what we wrote out here. This is meant to be the squared u d m minus 1 v. So that was an error. So let's correct that. The square u d m minus 1 v. All right. So I hope you get that. We started off by identifying this. We wrote out for this particular one, m combination 0 multiplying this, and that is this expression, okay, for the m plus 1v. And then we identified this, the u, the mv. You see that the u, the mv is here and it's here. So we added these two coefficients, and that gave us this m combination 0 plus m combination 1. Then we have the u, the mv. Then the next thing we add was, now that means we've taken this two. The next thing we add was the square u, the m minus 1v. So that is the same thing as what we have here, the square u, the m minus 1v. So that's what we just corrected now. It's meant to be the square u, the m minus 1v. And the coefficient will be m combination 1 plus m combination 2. So that is that. And for the, and I mean, the pattern continues like that. And for the last two, we did the same thing, just observe those things that are common and put them together. So this is the last term for this expression. All right, so how do we now conclude that? Now we have seen something quite clearly, that the order of the derivative for u goes from 0 to 1 to 2, and then it keeps increasing like that up to m and then up to m plus 1. So that's quite easy to observe. And the order for v, it goes from plus 1 to m plus 1 to m minus 1. We can see that it keeps decreasing by 1 as we progress, and then finally it gets to 1 and then goes to 0. So that is what we expect of this formula. Normally, if this formula was applied, we would expect that to happen. Okay, so the only thing that we have to worry about now, we can already see that as far as the derivatives are concerned, they actually align with the Leibniz formula. So the only part we have to justify for ourselves or convince ourselves about are the coefficients. Are these coefficients really what we expect of the Leibniz formula? So we will verify that now if these coefficients are the things that we expect for the Leibniz formula. Okay, so don't forget that we should have a picture of our destination in mind. So we expect that if we are to use the Leibniz formula for the m plus 1, okay, the m plus 1 of uv. This is not part of the solution. I just want to write out the rough work so you know what we are working towards or we are driving at. So this is meant to be the summation from r equal to 0 to m plus 1. You know, it should stop at m n or whatever we have here. So in this case, we have m plus 1 here. So it should stop at m plus 1. And it should be m plus 1 combination r, then the r u, then this will be m plus 1 minus r v. So this is what we expect this expression to be, meaning that if we are to go this way, the first term will be m plus 1 combination 0, and this one will now be the 0 u, and it will be the m plus 1 v. Okay, and then the next term will be, when we take our r was 0 for the first term. Okay, so if we take our r to be 1, we're going to have this to be m plus 1 combination, and this will be r was 0 here, this is now 1, so this will be 1. Then we are going to have this to be the 1 of u, then the m plus 1 minus 1, that is m of v. And then if we go ahead, the third term will be m plus 1 combination 2. R is 2 for this case, and this will be d to power 2 u. And then we're going to have this will be m plus 1 minus 2, that will be m minus 1, okay, v. And then it's going to move on like that. Plus, when we get to the final stage, we know the final one is when we have n plus 1. Okay, when we have r to be m plus 1. So before the final one, r will be equal to m. So in that case, we're going to have m plus 1 combination m. Then, because our r is m, we're going to have this to be d m of u. Then this will be m plus 1 minus m. That will be 1 of v. Then plus, when r is m plus 1, that will be m plus 1 combination m plus 1. Then we have this to be dm plus 1 of u, then the 0 of v. That's m plus 1 minus m plus 1. So to give us the 0 of v. So it's if it satisfies the Leibniz formula, or if it confirms the Leibniz formula, then we should look forward to an expression like this. So by what we have done so far, we can see that we have something similar to this, in that for the powers, look at the first term now. For the first term, we have the 0u, the m plus 1v. So that is exactly what we have here, the 0u, the m plus 1v. So that is correct. Okay. The next one is the 1u, the mv. And we have that here, the 1u, the mv. So that is correct also. The next thing is the square u, the m minus 1. You see this also to be the squared u, where is that, the squared u, that's here, the m minus 1v. So we can see the squared u, the m minus 1v, that is here, the square u, the m minus 1v, as expected. Then for the last portions, the last two terms, we know there are several terms in between, but for the last two terms, you can see the mu, the v, and that is what we have here, the mu, the 1v. And then lastly, we have we have the m plus 1 u, the 0v. So this is the m plus 1 u, the 0v. So as expected, if we made use of the Leibniz theorem or Leibniz formula directly, we would expect these terms to be exactly as they are now. The only thing we have to now convince ourselves about, as I said earlier, are the coefficients. That is, can we really say that m combination 0 is the same as m plus 1 combination 0? That is the issue. We can see that the coefficient of the 0u, the m plus 1v here is m plus 1 combination 0. So can we say that this expression here is the same as this? That's the problem. Okay, going further also, can we say that this m combination 0 plus m combination 1 is the same as this? That's what we have to establish now. Is it the same thing as m plus 1 combination 1? And for this also, can we say that m combination 1 plus m combination 2 is the same thing as m plus 1 combination 2? So those are the issues we have to deal with now. All right, so, and lastly, we can see that this last one should be m plus 1 combination m plus 1. Is it the same thing as m combination m that we have here? Okay, and for this one, this is meant to be m plus 1 combination m. Is it the same thing as this expression that we have here? So those are the issues we need to trash out now. So we now say that let's add an additional page to proceed. So we say that about m combination 0, by our definition, m combination 0 is meant to be m factorial all over m minus 0, okay, factorial, multiplied by 0 factorial. So we know that whatever this is just m factorial over m factorial multiplied by 0 factorial, which is 1. So it's basically 1. So it doesn't matter it's whether this was, so whether it is m combination 0 or m plus 1 combination 0 or n combination 0 or 5 combination 0, whatever it is, it's still going to give us 1, because we could as well just have this as m plus 1. So even if this was m plus 1 factorial over m plus 1 factorial 0 factorial, they will still cancel out, and this will still give us 1 anyways. So it is the same thing as m plus 1 combination 0. So it makes no difference. Okay, So we'll make that observation here and just take note of that. So let us say this is star. All right. Then the next thing we have to worry about is now we've cleared off, or we've cleared the issue with this coordinates, this coefficient rather. We can see that m combination 1 is the same thing as m plus 1 combination 1. Sorry, m combination 0 is the same thing as m plus 1 combination 0. Both of them will give us 1. So there is no issue with that. Okay, we'll come back to insert that here. Okay. So the for the next coefficients we see that for the coefficients we have left, we have m combination 0 plus m combination 1. We have m combination 1 plus m combination 2, m combination m minus 1 plus m combination m. You just see that what we have here is just m combination this. We have 0 here plus 1, it gives us this. This is 1 plus 1, it gives us 2. This is m minus 1 plus 1, it gives us m. So we observe that pattern. But we know that basically what we need to be certain of is the fact that it is equal to, let's say, m plus 1 combination 1 for this first one, for instance. And the general expression for what we have here can be written as, say, we have m combination, let's say, r minus 1, then plus m combination r. I mean, that's the general expression for the pattern of the coefficients we have here. M combination 0 plus M combination 1. So if our R is 1, for instance, this will be 1 minus 1. If our R is 2, for instance, this will be M combination 2, and this one will be M combination R minus 1. So that is basically what we have there for that pattern. So let's see, what will this give us? And we can begin to work rigorously and see what this should look like, or try to prove that it is actually equal to what we are driving towards, which is m plus 1 combination r. But we can easily also verify that it is going to be true, or it will be true, by using our calculator to check. For instance, if we try to check for, so let's just do some trial and error here to just verify what this is meant to be. So we try to do some trial and error here. Let's say we want to get 5 combination 0 plus 5 combination 1. Let's find out what is going to give us. If we try to get 5, let's say combination 1, 10 plus 5 combination 2. We try to find out what this gives us. And let's say we want to get another number, 6 combination 2 plus 6 combination 3. I mean, just following the same pattern, whatever this is, this will be one higher than it. So whatever this was, this will be one higher than it. So let's see what all of this will give us. We can check with our calculator. 5 combination 0. So let's move this here. 5 combination 0, that is 5. We have shifts. Then this is combination 0. Then plus 5 combination 1, that is 5. Then we have shift combination 1, and this is equal to 6. So you can see that this is giving us 6. And if we observe, look at what we're trying to drive at now. We expect that if this is going to be true, if it is going to satisfy this, we expect that something like m combination 1, m combination 0 plus m combination 1 should be the same thing as m combination, sorry, it should be the same thing as m plus 1 combination 1. So this is the point we're trying to make here. Let me put this here. So look at this. The coefficient of du, the mv here. That's it here. Du, the mv is m plus 1 combination 1. So basically, we expect that if we have m combination 0 plus m combination 1, it should give us m plus 1 combination 1. So if we have something like 5 combination 0 plus 5 combination 1, we expect it to give us 5 plus 1, which is 6 combination 1. So if we check 6 combination 1, for instance, is this the same thing as what we just obtained now? Sheet combination, where is combination again? Combination 1. Is that the same thing as 6? Yes. So we have been able to verify that it is 6 combination 1. So we see that this is the same thing as 6 combination 1. So let's note that. So, and if that formula is correct, we expect that, so I'll verify this. If that formula is correct, we expect that this will be 6, that is, we increase this one here. That will be 6 combination, the higher of the two, which is 2. And we expect that if this is correct also, we increase this by 1, that will give us 7 combination, the higher of these two, which is 3. So let's check if this will be the same. So let's check for each of these. 5 combination 1 plus 5 combination 2, that's 5 shifts combination 1, then plus 5 combination 2, 5 shifts combination 2, and that is giving us 15. So is that the same thing as 6 combination 2? Let's check what 6 combination 2, that's 6 shifts combination 2. So that is giving us 15 as well. So we have verified this second one. So this is also correct. And if we check for this also, 6 combination 2 plus 6 combination 3, that is 6 shift combination 2 plus 6 shift combination 3, that is equal to 35. Let's check if it's the same thing as 7 combination 3. This is 7 shifts and combination and 3, then that's 35. So I've verified this as well. So basically we will just state without proof here, because that's not our main problem, that this is basically going to be equal to m plus 1 combination r. We'll pick the higher one, we'll add 1 to what we have up here. Now we'll pick the higher one of these two, since the difference is 1, we'll pick the higher of the two. That's basically what we've done here. Add 1 to this is giving us 6. The higher of 0 and 1 is 1. Add 1 to this, it gives us 6. The higher of 1 and 2 is 2. Add 1 to this, it gives us 7. The higher of this and this is 3. So this is a general observation about combination. So we can call this equation star star. Okay. So we have verified that equation star star is actually true. So we can you can also play around with doing a rigorous proof of that. Okay. By writing out expressions for this, you can write out the expression for this when you interpret this combination and add them up and see that they are going to be equal to this. You can also decide to play around with a proof by mathematical induction for this relationship. Okay, so having established these two, okay, by this equation star and star star, we can now return to this expression here and just conclude that this our the m plus 1 of uv, don't forget this is the m plus 1 of uv. This is what we were still dealing with. All right, so we can now come back here and say that this coefficient here is going to be m plus 1 combination 1. This one is going to be m plus 1 combination 2. This will be m plus 1 combination m. This will be m plus 1 combination sorry, that's just m plus 1 combination m plus 1, because m combination m doesn't matter what m is. 1 combination 1 is the same as 2 combination 2, as 3 combination 3, as 4 combination 4. So m combination m is the same thing as m plus 1 combination m plus 1. So there is no further check about that. But we can write it out anyways, that if we have m plus m combination m, so just like m combination 0 was m plus 1 combination 0, so if we have something like m combination m, that is m factorial over m minus m factorial multiplied by m factorial, and that's basically the same thing as m plus 1 factorial, because this is going to cancel, m factorial is going to cancel m factorial. This m minus m is 0 factorial, so basically this is 1 over 0, 1 over 1, which is 1. Okay, and this is just the same thing as having m plus 1, or even anything at all, factorial divided by m plus 1 minus m plus 1, that's minus m minus 1 factorial, then m plus 1 factorial. So it will not make any difference, this will still give us 1 anyways. So basically whether it is m combination m or m plus 1 combination m plus 1, they are the same. So we can call that equation star star star. Okay, so now we're good to go. So let's say that this was equation let's say a. So we can now go back to equation a and make these substitutions, make these observations that we've just written out here. So we can now say that substituting all of this into equation A, we will have the m plus 1 of uv to be equal to, so we pick those terms up one after the other now. This is the m plus 1 of uv. We simplified it up to this point. Now we have seen that m combination 0 is the same thing as m plus 1 combination 0. So we're using all of that here. So we see that substituting, so what we're doing here is substituting the observations in star, 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 and star, star, star into equation A. So this is equation A. Into this equation, it gives us this into equation A, will give us this expression. So let's wipe this off from here. Right. So this is going to be m plus 1 combination 0 and d to 0 u, then d to m plus 1 b. So that's basically what we have up here. That's what we are repeating. Okay. That's basically what we have up here. Just change this to m plus 1 combination 0. Every other thing remains as before. Then this m combination 0 plus m combination 1, that will be m plus 1 combination 1, okay, by our equation star star. So we know that when we have something of this nature, of this form, it's just m plus 1 combination r, which are the higher of the two. So the next one will be plus m plus 1 combination 1, then d1 u, then dmb. So and then the next one will be plus the next one. When we apply equation star star to the next one, this will be m plus 1 combination 2. So this, as expected, will be n plus 1, m plus 1 rather, combination 2, then d squared u, d m minus 1 b. So it keeps decreasing. This keeps increasing from 0 to 1 to 2 and so on, while the power of this keeps decreasing from m plus 1 up to 0. So this pattern continues like that and like that. Plus, then we'll pick the last two terms. So for the last two terms, we have m combination. Where is this now? We have m combination m minus 1, that will be m plus 1 combination m. Okay, so that will be m plus 1 combination m. So this is m plus 1 combination m, then the m of u, then d1 of b. Then finally, we're going to have m plus 1 combination m plus 1. So since we already know that what we have up here, which is m combination m, by our equation star star star, okay, this equation star 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 is the same thing as m combination m plus 1. This is m combination m plus 1 into d0 u, then d0, that will be the m plus 1 u, then d0 b. So that is that about that. So come a long way. So we now see that our our relationship is also true. That is, the formula is true for n equal to m plus 1. So we have been able to establish that it is true for n equal to m plus 1 because this is basically equal to, that is what we have just obtained now. We can already see the pattern that this is simply equal to what is provided for by the Leibniz formula, which is that here we took the summation from 0 and ended it at m plus 1. So this is from r equal to 0 to m plus 1. So we have been able to see that. And then we had m plus 1 combination. So this was m plus 1 combination r starting from 0. And then d r of u, then d m plus 1 minus r of b. So we see that this is the same thing as what we have up there. This is what is provided for by the Leibniz formula, and that is already established here to be true for when n equal to m plus 1. So we now say that thus the statement is true for n equal to m plus 1. The statement is true for n equal to m plus 1. So having established that, that means we've concluded all the necessary steps for our mathematical induction, so proof by mathematical induction. Please, this the reason I've put this in this rectangle is because it is not part of the solution. This was written out so that we would see where or what we are driving at, okay, as we always did. So that's why it is put in rectangle, just to show you that it is not part of the main flow of the problem. You can see this as some rough work. Why we wrote it out again is so that we will see what exactly are we trying to establish, so that we know how to proceed from here. And so with this, we're able to tell what the coefficients should look like, and then how we could arrive at them, how we could verify them, which we did by equation star 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 and star star star. So that is that about that. So now we've concluded the last step required for mathematical method proof. So we have been able to see that the statement is true for when n equal to 1. We've seen that here. We've assumed it is true for n equal to m, and by that result, by the results for when it is true for n equal to m, we have now proceeded for what will happen for when n equal to m plus 1. Okay, making use of the result above, we operated on it normally, we obtained this result, and we're able to verify that this result is the same as what would have been given if we applied the Leibniz's formula directly. So that's what we've done here. So I've been able to see that the statement is true for n equal to m plus 1. So finally, we can now see that hence, indeed, the n of uv is actually equal to the summation from r equal to 0 up to n of n combination r into the r of u into the n minus r of v. So that is that about that. So this has now been proven. So we know that it is true. So that's that about this lesson. One final thing before we go, you should also know that when you have n combination r, it can also be written in this form, n bracket r. So if you see something like this in your textbook or any other material, know that they are referring to exactly the same thing, n combination r. So this is another way to write n combination r. That means I could as well write this rule as follows. I could write this as the n uv equals summation from r equals to 0 to n of n r. Then I have this to be the r u, then the n minus r b. So if you see this in any material, it refers to the same thing, the concepts remain the same, and all of the things we've done remain valid. Okay, all right, so that is the end of this lesson. We'll proceed from here in the next lesson. Thank you for watching. Please go through this again, look at it again, work it out and see it for yourself. If there are still issues with it, please ask me in the chat room if there is any part that is still not clear, so that we can have a look at it, probably in one of our live meetings. Okay, thank you.